Hello to everyone. This is Shantan Kumar, Assistant Professor, Department of Mathematics, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. The subject is matrices and calculus. Today we are going to discuss the topic on discussion of tutorial question bank module 2 eigenvalues and eigenvectors. This is under the subject matrices and calculus, and here first we will go to discuss what is the syllabus of this module 2, that is based upon the eigenvalues and eigenvectors. Here first of all, the syllabus is under here eigenvalues and eigenvectors. We are going to covering, that is eigenvalues, eigenvectors and their properties. Here the properties are, we are going to discuss that without proofs, and also the Cayley-Hamilton theorem, that also we are going to discuss the without proof, and verification, finding the inverse and powers of the matrix by Cayley-Hamilton theorem, and finally the diagonalization of a matrix. For the purpose of this one, if you want to go to discuss, that is a model question bank based upon this unit, this is the module 1, this is the module 2. First of all, we need to understand clearly how to find the eigenvalues, eigenvectors, and before that, what is the concept of, that is a linear dependence, linear independence, and what are the properties on the eigenvalues and eigenvectors. And also, what is the Cayley-Hamilton theorem statement? Based upon that, what are the properties of the Cayley-Hamilton theorem, and finally we'll discuss, that is a diagonalization of a matrix. That means we are going to discuss all these things regarding the main topics, like main formulas. Here the first one, what is the meaning of the linearly dependence, linearly independence? That means how to identify the linearly dependent and also linearly independent of a matrix or of a vectors. Here, according to the definition of the linearly dependence, whenever we are going to finding the determinant, if the det is equal to 0, that means whenever the det is 0, that is nothing but it is called as linearly dependence, and other terminology, it is a singular matrix or singularly vectors. And another one, that is a linearly independent. The linearly independent is nothing but whenever the determinant is not equal to 0. That means it is called as a non-singular, and also it is called as a linearly independent of a matrix. And based upon that, we need to further continuation, that is eigenvalues and eigenvectors. And in that also, first of all, we will go to discuss in that the eigenvalues and eigenvectors, what is the characteristic equation, what is the characteristic matrix, and characteristic values, and again characteristic vectors. That means these are the interlink one by one the terminology. First one, what is a characteristic equation? And that also, that is based upon the characteristic matrix, that is a characteristic polynomial, and that then only characteristic equation. That's why we need to discuss that what is a characteristic matrix. And according to the definition of the characteristic matrix, for example, let us assume that A is any matrix, that is a square matrix. Here consider A11, A12, A13, A21, A22, A23, A31, A32, A33 be any square matrix. Like related any by 2 by 2 is also, we need to assume that is a 2 by 2 is also square matrix. And again the continuation, we need to assume that I be any unit matrix, that is identity matrix. Corresponding that, consider the matrix A, it is a 3 by 3 matrix. We need to assume that I is also 3 by 3 identity matrix. And also lambda be any scalar. Lambda be any scalar. And based upon here A, lambda, and also I, if it is a consider A minus lambda I, that is nothing but we obtain that finally in the matrix notation, that is a characteristic matrix. That means with the help of the consider matrix A, and also lambda is a scalar, and also I is any identity matrix, with the help of that A comma lambda comma I, if it is obtained within the matrix, that is A minus lambda I, it is called as a characteristic matrix. And further based upon this one, if it is finding the det, that means det of A minus lambda I is called, that is a characteristic polynomial. That means first is we need to find out what is a matrix, and after that we need to find out that is a determinant, that is a characteristic polynomial. And whatever we obtain the polynomial, if it is equating the 0, that means the det of A minus lambda is equal to 0, called that is a characteristic matrix equation. These are the one by one interlinked with the given matrix A, and again the lambda is a scalar and I is also identity matrix. With the help of that, first we need to find out the characteristic matrix and characteristic polynomial, and also that is a characteristic equation. That means matrix notation is obtained, that is a characteristic matrix, and determine the polynomial equation is nothing but the characteristic polynomial. By equate that is equal to 0 is called as a characteristic equations. And with the help of this one, we need to further, that is a finding the eigenvalues and also eigenvector. Now we'll go to discuss, that is with the help of that one example like 2 by 2 matrix, simple, that is easy to understand, characteristic matrix, characteristic polynomial, and also characteristic equation. Here, according to, for example, let A be any square matrix. Here with example, it is a 2 by 2 matrix. For example, here corresponding that A is a matrix, it is 1, 2, 3, 4, and then lambda is any scalar. I is also considered, that is a identity matrix, order is a 2, that is 2 by 2, and based upon that A minus lambda is within the matrix, that you obtain that 1 minus lambda, 2 and 3, 4 minus lambda is called, that is characteristic matrix, that we obtain in terms of the matrix only, characteristic matrix. And further, characteristic polynomial, that means same whatever the given matrix and lambda and identity matrix, and with the help of that, if it is obtained that delta of A minus lambda, like that 1 minus lambda minus 2, 4, 1 minus lambda, we need to find out what is the delta of this matrix. That means we obtain in that polynomial is called as a characteristic polynomial. And with the help of the characteristic polynomial, by equate that is equal to 0. That is equal to 0 means it is a whatever the same example, with the help of 1 minus 2, 4, 1, we obtain that equation. That equation is treated as is equal to 0. That is a characteristic equation. These are the interlinked one by one, characteristic matrix, characteristic polynomial, characteristic equation. And based upon this one, further it is eigenvalues and eigenvectors, and again now that we'll go to discuss definitions. And before that also, here the matrix is a 2 by 2. While we are finding the delta of A minus lambda is equal to 0, we obtain the equation. And 3 by 3 is also we obtain the equation delta of A minus lambda I. While we are going to calculating the equation with the help of the 2 by 2, under that we given that here, that is lambda square minus s1 lambda plus s2 is equal to 0. Actually it is s2r, it is a delta, both are same. It is s1 is a trace of the matrix and s2 is the determinant of the given matrix. This is the meaning of under the 2 by 2. And again, yes, under that polynomial, that is a 3 by 3, that is lambda cube minus s1 lambda square plus s2 lambda minus s3, like according to 0. This is nothing but s3. Both are same. And s1 is nothing but under the 3 by 3, the trace of the matrix. s2 is the sum of the cofactors of the diagonal. And s3 is the determinant of the given matrix. These are by equating the delta of A minus lambda equal to 0, we obtain this is the equation. Easy to calculation with the help of this is the clear formula. Regarding all these things we discussed in the previous sessions clearly, how to find the eigenvalues and how to find the eigenvectors, and briefly we discuss in the each and every lectures. But this is the question bank only. Based upon that, we'll go to discuss the outlines of what are the topics which is covered and what we discussed in the previously, that is the formulas based upon these are the conditions. These are the recall the conditions. And here further eigenvalues and eigenvectors and what are the node conditions. Here according to that, eigenvalues is nothing but whatever we in the previous slide, that is a characteristic equation. By getting the characteristic equation, solve that. While we are solving that equation, we obtain the values. That values are called the eigenvalues. That means it is the roots of the characteristic equation is called the delta of A minus lambda is equal to 0 is called, that is the eigenvalues of the given matrix. And again, for example, the 2, 1, 3, 4. Here the equation is characteristic equation is lambda square minus 6 lambda plus 5. That means it is a 2 minus lambda 1 and 3, 4 minus lambda. By equating this one, we obtain this is the equation. By solving this equation, we obtain values. This is the 2 by 2 matrix. While see we are solving this is the 2 by 2 equation, we obtain the two solutions. Here the solutions are 1, 5. That 1, 5 is nothing but these are the two roots. The two roots are called as here, that is eigenvalues. And similarly, the eigenvectors corresponding these are the matrix. That means if lambda is an eigenvalue of the square matrix A, if there exists a non-zero vector x such that then Ax is equal to lambda x, with the help of this one, by equating that, we get that eigen corresponding, that is a vector. That is a corresponding value of lambda. That means if the matrix are eigen 2 by 2 matrix, we obtain the two eigenvalues. We find out that is a two eigenvectors that is corresponding that lambda 1, lambda 2. And this is the procedure under the Ax is equal to lambda x. Here further, it is vector must be a non-zero vector. That means while we are going to calculating corresponding eigenvalue, that is eigenvector, we are not getting any the zero eigenvector. It should make a must and should satisfy the non-zero eigenvector. It is a must and should, it is satisfied. And again, for example, if lambda is an eigenvalue of the matrix A, if and only if there exists a non-zero eigenvector x such that Ax is equal to lambda x, that is, if x is a eigenvector of the corresponding A, that is eigenvalue of lambda, kx is also eigenvector corresponding that eigenvalue. These are the some common things we need to remember, that is a general conditions only. And further, here are the node conditions. That means whatever we obtain, these are eigenvalues. The eigenvalues are called as a sometimes it is a proper values, and again the latent values, and also that is a characteristic values and eigenroots. These are the synonyms for the eigenvalues. That means one is a eigenvalues are also known as eigenroots or characteristic roots or characteristic values, and again latent roots are proper values. These are the some synonyms for the eigenvalues. In sometimes it is like called as according to these are the synonyms. And further, we need to discuss based upon the eigenvalues and also eigenvectors here. What is the procedure to find the eigenvalues and also eigenvector to that 3 by 3 is a matrix. That means how to find that. That means actually one of the slide is showing something according to that. That is the equation we obtain, that is a 3 by 3, that is lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. But here, according to what is the working rule in that 3 by 3 matrix. That means according to find out what is a characteristic equation, that is lambda cube minus s1 lambda square plus s2 plus lambda plus minus s3 is equal to 0. And here that s1 is nothing but here find that roots of that lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. That means we need to find out what is a s1, s2, s3, and again after that what is the eigenvalues, that is lambda 1, lambda 2, lambda 3. That means this is the working rule to find out the eigenvalues and the eigenvectors. And again here, that eigenvalues are here nothing but lambda 1, lambda 2, lambda 3. And again that with the help of that here, that 3 by 3 matrix, that is the 3 eigenvalues. Here we need to find out one by one, that is the corresponding eigenvalues, eigenvectors. That is lambda 1 eigenvector and lambda 2 eigenvector. That is with the help of that, that is indirectly x is equal to lambda x, and it is a case 1 ax is nothing but lambda 1 into x, and based upon this one, a minus lambda 1 into I into x is equal to 0. This equation only we obtain according to this terminology. Either here we need to solve that eigenvectors, either two methods. One is a equation method and otherwise it is a Gauss elimination method. The two methods it is possible to find that eigenvectors. And again further, with the help of that eigenvectors is nothing but the solution of a x of a above system. That means with the help of the a minus lambda I, that is the third equation, by solving the Gauss elimination or matrix equation method, we obtain the values. That values are called as eigenvectors corresponding that lambda 1 is a eigenvalue. And again after that we need to repeat that lambda to lambda 3, like according to that 1, 2, 3, 4 steps we need to continue. That is a fifth point also. That is a corresponding the rest of the eigenvalues we need to find out that eigenvectors. And again here, what are the properties after finding that eigenvalues and eigenvectors? Is there any properties of eigenvalues and eigenvectors? Here that is the properties of eigenvalues and eigenvectors. This is also very very important to understand. If we understand that properties, then easy to calculate that further proceeding the conditions. Here what are the properties of eigenvalues and eigenvectors? Here for example, if it is assumed that matrix form, and again what is the name of the matrix, and again what are the particular matrix eigenvalues. Here for example, the matrix is nothing but that is under the 2 by 2. We need to assume that A0 0 being it is a matrix in name is a diagonal matrix, because of the non-diagonal element should be 0. Based upon the matrix is said to be the diagonal matrix. Whenever the matrix is directly given the diagonal matrix based upon the property, it is a eigenvalues of the given matrix if it is satisfied with the diagonal matrix, therefore the diagonal elements. That is the meaning of the diagonal elements. Here the diagonal elements are clearly A comma B. And further, the matrices are A, B and 0 and also D. And here also, while we are going to observing, this the matrix is suitable for the upper triangular matrix because of it is a below the diagonal element should be 0. Here in that first case, it is a diagonal matrix, and in this, it is a upper triangular matrix. Whenever the matrix is upper triangular matrix, the eigenvalues are clearly satisfied the diagonal elements. That means whenever the matrix is the diagonal matrix are also the diagonal elements. If it is upper triangular matrix is also the eigenvalues of the matrix is the diagonal matrix. And further, the matrix is a like according to this such type of this matrix. That means it is also the matrix is a lower triangular matrix. The matrix is a lower triangular matrix. It is also the eigenvalues of the given matrix are the that is the diagonal elements. Here also A comma C is the diagonal elements. That means based upon these are the observation, we can identify the matrix is either the diagonal matrix or the eigenvalues are diagonal elements. The upper triangular as well as the lower triangular matrix are the diagonal elements are the eigenvalues of the matrix. This condition is must and should it is satisfied. And again next further, the matrix is in the form of 3 by 3 for example. That 3 by 3 matrix is also, in this matrix, it is a clearly same like that according to the 2 by 2. It is also satisfied the diagonal matrix. Here also the diagonal matrix are nothing but based upon the previous 2 by 2. The diagonal elements are the diagonal matrix. Here therefore the diagonal elements are it is ADF. Therefore the eigenvalues are also ADF. And further similarly like that previously the 2 by 2. The matrix is a upper triangular matrix. Therefore, the diagonal elements are, it is a matrix is satisfied with the upper triangular matrix. Therefore, the eigenvalues of the upper triangular matrix are also the diagonal elements. Therefore, ADF is a diagonal elements. And further, the matrix is a like same that 3 by 3. It is a lower triangular matrix. That means under the 3 by 3 that is a lower triangular matrix. Therefore, it is also the diagonal elements are the eigenvalues of the given matrix. Therefore, it is here A comma C comma F are the eigenvalues of the particular given matrix. Therefore, based upon these are the some of the basic example like by the properties we can define that what are the eigenvalues without calculating that delta of A minus lambda is equal to 0. And for example, the other properties matrix and again that some eigenvalues, then corresponding what are the properties based upon this one. For example, you need to assume that A is a matrix. Your eigenvalues are, if it is considered lambda 1, lambda 2, lambda 3. That means we need to remember in our mind the the given matrix is a 3 by 3. The eigenvalues are 3, that is a lambda 1, lambda 2, lambda 3. And here matrix, for example, A is a matrix. That particular eigenvalues are minus 1, 2 and also 5. That means it is a particular eigenvalue of lambda 1 is equal to minus 1 and lambda 2 is equal to 2 and lambda 3 is equal to 5. And based upon this, the 3 by 3 is the given matrix. Here, the sum of the properties, one is A transpose. That means we need to observe that lambda 1 transpose and lambda 2 transpose, lambda 3 transpose. That means there is no change of the transformations. And based upon here, the transpose of the eigenvalues are also, there is no change. Because of lambda 1, lambda 2, lambda 3, we are not changing any value. Therefore, minus 1, comma 2, comma 5 is also, we are not going to changing the values. Therefore, A transpose is equal to here also minus 1 and 2 and also 5. While we are going to observe here, it is there is no change. It is lambda 1, lambda 2, lambda 3. Here, minus 1, comma 2, comma 5 eigenvalues. And similarly, the eigenvalues are k into here. That means whatever the eigenvalues are lambda 1 is a k lambda 1, k lambda 2, k lambda 3. That means we are multiplied with k lambda 1, k lambda 2, k lambda 3. That whatever the origin of the eigenvalues, and here also 4 into a. That means we need to observe that here k is nothing but it is a 4. Therefore, that 4 into lambda 1 is a 4 into minus 1, that is a minus 4. 4 into 2 is a 8, that is a 8, and 4 into 5 is a, that is a 20. Because of it is a 4 into, that is minus 1, and 4 into 2, and 4 into 5. These are the from the given matrix origin we obtain the values. And similarly, it is a is a matrix is these are the matrix same like that. And further, it is A inverse is equal to A inverse is nothing but here 1 by lambda 1, 1 by lambda 2, 1 by lambda 3. And based upon that, inverse that is nothing but 1 by A. 1 by A is nothing but here also 1 by minus 1 is nothing but minus 1, 1 by 2, 1 by 5. Because of it is 1 by minus 1. 1 by minus 1 is nothing but it is minus 1 only. Due to that reason, we need to observe that properly. Whatever the eigenvalues of the given matrix, the inverse of the eigenvalues are also the reciprocal of the given matrix. And similarly, A power k. A power k is nothing but it is the lambda 1 power k and lambda 2 power k and lambda 3 power k. That is minus powers of the eigenvalues. And similarly, for example, A power cube. That means it is minus 1 whole cube. Because of it is a minus 1 whole cube is nothing but it is minus 1. And again it is nothing but 2 whole cube is nothing but that is 8. And again further it is a 5 that is a whole cube is nothing but 125. This is nothing but the powers of the eigenvalues. Whatever the eigenvalues of the given matrix, the power of the eigenvalues are also same the eigenvalues of the matrix. These are the some properties we need to remember or understanding the properties of the eigenvalues. And further, same like that. We need to remember here already, these are the remember the conditions. The eigenvalues are also known as the latent roots and proper values and eigenvalues and again like all these conditions we need to remember. And sum of the eigenvalues is equal to. And this is also very important to remember the conditions while we are going to calculating whether the eigenvalues are correct or wrong, that we need to cross verify with the help of the sum of the eigenvalues is equal to that is a trace of the matrix. That is a trace of the matrix. And similarly, the product of the eigenvalues. The product of the eigenvalues are also we need to remember that is a determinant of the given matrix. Determinant of the given matrix. While we are going to calculating any check the cross verification, whatever we obtain the eigenvalues is equal to the sum is equal to the trace of the matrix and product is equal to the data of the matrix. These are the very important to remember the conditions. And here, if one of the eigenvalues is 0, for example, if while we are going to finding the data of m minus lambda is equal to 0, for example, if we get the value lambda is equal to any one of the eigenvalues 0, that time the inverse does not exist. The inverse does not exist because of whenever the matrix eigenvalues is 0, then automatically it is not existed because of here A inverse is equal to that is adjacent of A by the data of A, and it is adjacent of A is okay, but data of A is equal to 0, therefore it is equal to infinity, therefore it inverse is does not exist. This is the meaning of whenever the eigenvalue one of the eigenvalue is 0, the inverse does not exist because of that A is a singular matrix. And that means the matrix is a singular matrix, automatically the inverse does not exist the conditions. And further, we need to remember these are the conditions. Next further, what is the Kelly-Hamilton theorem? The Kelly-Hamilton theorem, it is a statement only required, it is a proof is not required. Here, based upon the Kelly-Hamilton theorem statement, again we need to discuss the applications of the Kelly-Hamilton theorem. And based upon the applications here, it is one is to finding the inverse of the matrix and to finding the powers of the matrix. That means one is the powers of the matrix or otherwise it is a inverse of the matrix. That means based upon the Kelly-Hamilton theorem, these are the two applications. One is finding the powers and second one is inverse of the matrix. Next year, under the procedure of the Kelly-Hamilton theorem, what is the working rule? Under the 2 by 2 matrix. If you understanding the 2 by 2, the 3 by 3 is also same the conditions to finding the verification the Kelly-Hamilton theorem and finding the powers and inverse of the matrix. For example, the statement of the Kelly-Hamilton theorem. And as per the statement of the Kelly-Hamilton theorem, every square matrix, that means any given square matrix which satisfies the characteristic equation. That means every square matrix satisfies its own characteristic equation. That means, for example, if you get that is applying the data of m minus lambda I is equal to 0, we obtain in that is lambda. For example, 2 by 2 it is nothing but lambda square minus s1 lambda plus s2 lambda is equal to 0. and here it is nothing but S1 is a trace and S2 is a data of the matrix. That means we obtain that finally in the lambda. Therefore, find them according to the characteristic equation of the matrix, that according to that is a data of m minus lambda is equal to 0. And after that, we need to replace that. That means the data of m minus lambda is equal to 0. For example, it is our equation is lambda square minus s1 lambda plus s2 is equal to 0. That is the first condition. And second condition, put lambda is equal to a. That means in that whatever the equation you put lambda is equal to a, that is a square minus s1 a plus s2 into I is equal to 0. That we need to show that conditions. And again here, how to find out that whatever the equation that is we need to find out what is a square, because of in that required that a is a given, that a square we need to find out from the given equations, from the given matrix. And again after finding that a square and a and also unit matrix, we need to replace in this, and again this equation is clearly satisfied the given problem. That is the meaning of under the verification of the Kelly-Hamilton theorem. And further, if you want to find out the A inverse, the equation is multiplication by A inverse, then find the solutions. While we are going to discuss that regarding this, all these things we discussed in the previous lectures clearly to verification of the Kelly-Hamilton theorem and finding the powers and applications of the conditions. Here under the 3 by 3. Under the 3 by 3 is also same the statement every square matrix satisfies its own characteristic equation. And further, first we need to find out what is the characteristic equation, and after that we need to replace lambda is equal to a, and further find out a square and also a cube by using the given matrix A. And again after that we need to replace in the whatever the characteristic equation, then again automatically the equation is verified. And finally we need to find that A inverse here by the multiply with the equation A on both sides A inverse. We obtain that clearly, that is inverse of the matrix. And while we are going to finding the powers are also same based upon this one, we need to find the solutions. Multiplying with a power n, m minus n on both sides. Here, next is the last, the concept based upon this is the diagonalization of the matrix. The diagonalization of a matrix is nothing but whatever we completed, that is a characteristic equation, with the help of that equation only we need to find the solutions. Otherwise, we need to find out what is the first eigenvalues and also eigenvectors, and also based upon that, we need to find out that d is equal to p inverse into AP. That means first to find out that characteristic equation, and again that finding the eigenvalues and eigenvectors, and again the model. Under here, we additionally the topic is which is based upon the model matrix, and again regarding all those things. Here, first thing. If a square matrix A of order n has a linearly independent eigenvector, that is such that x1, x2, up to xn corresponding to the eigenvalues lambda 1, lambda 2, lambda 3. And again then the matrix P can be formed such that that is a P inverse into A into P is equal to diagonal matrix. And what is the meaning of this? All these things. That means first we need to find out the eigenvalues, and again after that corresponding eigenvectors. Then we need to construct it within the matrix that is a P, then that is a model matrix, and again after that we need to find out P inverse, and again the product of P inverse into A into P, then the resulting diagonal matrix is called, that is a diagonal, what is a diagonal matrix. Here it is denoted, that is D is equal to P inverse into AP, where P is called as a model matrix. P is known as a model matrix. The model matrix is nothing but the collection of eigenvectors. And these diagonal matrix is also known as, sometimes it is a spectral matrix. Diagonal matrix whose the diagonal elements are clearly satisfied the eigenvalues of the given matrix. That means these are the three things we need to remember. One is the formula of D is equal to P inverse into AP, and P is known as a model matrix, and D is known as a spectral matrix, and resulting diagonal matrix is called as a, that is the eigenvalues of the given matrix. And here what is the working rule under this one? First, it is a matrix is a diagonalization. If it is similar to the diagonal matrix, then it can be found such that that is a P inverse into A into P is equal to that is a diagonal matrix. Here it is a D is the, that is the eigenvalues of the given matrix. Spectral matrix. And finally, remember when it is possible to diagonal matrix. That is also important thing. all the matrices are not at all diagonal agent. That depend upon we need to find out the eigenvalues corresponding the eigenvalues, the eigenvectors. When we are going to observing that algebra multiplicity and geometric multiplicity of that particular eigenvalues is both are same, then only it is a diagonalization matrix is accepted. That means diagonalization possible matrix is a possibilities. Here another condition, linearly independent eigenvectors are also the diagonalization of the matrix. Distinct, no problem. AM is equal to 0. That means here mainly we need to remember the diagonalization is possible if and only if the linearly independent eigenvectors. Second condition is if eigenvalues are different also, the matrix is a diagonalization possible. And the third condition, the algebra multiplicity and geometry multiplicity, both the conditions are same, then only the matrix is the diagonalization of a matrix. These are the three conditions we need to remember whenever the matrix is the diagonalization. These are the three conditions are equal to satisfied. That means we need to check it if any one of the condition it is existed. Yeah. First, finding the eigenvalues, we need to check that if all the eigenvalues are different, then the matrix is the diagonalization. That is the first condition. If sometimes it is eigenvalues are repeated, sometimes that means at that time we need to find out what is the algebra multiplicity and geometry multiplicity. That particular eigenvalues, whatever the eigenvalue is repeated, that particular eigenvalues only we need to check that AM and GM. And in case AM and GM both are the same, then it is a diagonalization. If particularly AM is not equal to GM, then it is not a diagonalization of a matrix. Finding this is the procedure to finding the P inverse. Yeah, this is the procedure to find out. This is also very important to finding the diagonalization of the matrix power. And we know that that is a D is equal to P inverse into AP. For example, D square is that P inverse into A square into P, and D cube is a P inverse into A cube into P. Similarly, D power n is also P into D power n, A power n, and P inverse into A power n into P. And from this, if we need to find out that A power n, that is multiplication on both sides, that is a P, then automatically that A power n is nothing but the value is a P into D power n into P inverse is the formula. Yeah, this is the clear thing. Yeah. Now we'll go to discuss that is a question bank, our target, what we are going to discuss the today's session. Based upon the previous that summarize that total the module 2, then easy to survey this the model question bank like that. And under here the model 2 like that question bank also like the same last session, the model 1 question bank. Part A that is a 10 critical thinking, and part 2 part B is that is a essay type question 20, and part C is the short type of questions problems. Here first one, verify the Cayley-Hamilton theorem. Here also that is a problem. While we are going to observing, first we need to find out what is the Cayley-Hamilton theorem. Here we need to find out that a data of A minus lambda is equal to 0. We obtain that lambda 1 and also lambda 2 and also lambda 3. And again, it is data of A minus lambda is equal to 0. We obtain that the equation in the form of that is a lambda cube minus S1 lambda square. It is a 2 by 2 only. Therefore, under the 2 by 2, as we know that is a 2 by 2 lambda square minus S1 lambda plus S2 is equal to 0. And here S1 is the trace of trace A, and S2 is the data of the matrix. We need to find out first lambda, and again after that we need to replace that lambda is equal to A, that is A square minus S1A plus S2 into I is equal to 0. Now we need to find out this verification. With the help of that here, lambda 1, lambda 2, as we know that here S1, S2, we know that is according to clearly given here. And we need to find out S1, S2 and again replace here. And after that, I is also we know that, and A is the given matrix A square. Here, that A square, we need to find out what is the value of A square. That A square is calculating A into A is the matrix. And based upon this one, Here we obtain that a square and a and also I. We need to replace in the equation, then which is satisfied. That is output is a 0 is a matrix. That means after that replacing all these values, we get the value of this one. And again after that, with the help of that one, again you need to find out what is the evaluate the conditions. This is important to think like that. Here based upon the simplification, while we are going to thinking the logically, we need to take out common, that is a 2a square, and again after that, and again a square minus 5a, and again minus 7, like like according to one by one all those things. Here something addition and subtraction is required, and again find the simplification, we get the solutions. And again next one, here using the Cayley-Hamilton theorem, find the a cube and a power minus 3. And here also the data of a minus lambda is equal same as to that previous one. It is equal to obtain, that is a lambda square minus s1 lambda plus s2 is equal to 0. And again it is a, we need to replace as per the Cayley-Hamilton theorem satisfied, means we need to replace lambda is equal, that is a, that is a square minus s1a, and again plus s2I is equal to 0. And from this equation we need to find out a cube. A cube is nothing but that equation is multiplication with a, then we get that a cube is the value. And again similarly a power minus 1, same on this equation, we need to multiplying with the a inverse, and again we get that a inverse, and after that again one more a inverse, and again one more a inverse, you find that a power minus 3 is the required solutions. Here you state the Cayley-Hamilton theorem, you find the eigenvalues and eigenvectors. State the Cayley-Hamilton theorem. That means as you know that every square matrix satisfies its own characteristic equation. That is a statement of the Cayley-Hamilton theorem, and after that finding the eigenvalues and eigenvectors. That means again after that you need to find out data of a minus lambda is equal to 0. We obtain that lambda 1, lambda 2, and lambda 3. And after that corresponding lambda 1 you obtain that x1 and again x2 and also x3, that is with the help of a minus lambda 1 into y, x is equal to 0. Based upon that you obtain, that is similarly, and again these are the eigenvectors. That is a corresponding eigenvalues to eigenvectors. And after that again that then find the eigenvalues. Eigenvalues is nothing but here it is a like the given matrix is upper triangular matrix. Therefore, based upon this one, the eigenvalues of A is equal to 1, 3, 2. And after that, properties of you need to applying what is A square and again A cube and also I matrix. Then we find the solutions. And again after that, by the properties of this one, we need to replace in these equations. And next one is the matrix is the diagonalization or not. Is the matrix diagonalization or not? We can't say directly. After that calculating, then only it is possible, because of the matrix is a satisfied, required satisfied AM and GM. Otherwise, the first we need to find out what is the data of A minus lambda is equal to 0. That is with the help of that lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. That as you know that s1 is a trace and s2 is a sum of the cofactor diagonal and s3 is equal to something determinant of the matrix. If eigenvalues are like lambda 1, lambda 2 and lambda 3 is a different the eigenvalues, then it will diagonalizable. In case the eigenvalues are repeated, we need to find out, or otherwise in case repeated, for example, the repeated eigenvalues, we need to check out what is a AM and also GM. In case both, then only the matrix is a possibilities. In case it is not same, AM is not equal same, it is a not a diagonalization of the matrix, that particular repeated eigenvalue. And next one, determine the model matrix. Here they are asking to find out model matrix. That means first we need to find out what is the data of A minus lambda is equal to 0. And again as per, that is lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. That means we need to find out what is the lambda 1, lambda 2 and lambda 3. And again corresponding that x1 and x2, x3 with the help of A minus lambda I into x is equal to 0. And again, whatever you obtain that x1, x2, x3, we can right consider x1 and x2, x3 is called as a model matrix. That is a model matrix is nothing but collection of 3 eigenvectors or collection of the eigenvectors simply. Next, determine the eigenvalues and eigenvectors. And also a power 4. That means it is also same like that up to here. The condition we repeat. Next, find the a power 4. That a power 4 is nothing but whatever the equation you obtain that is a cube minus s1 lambda a cube and again plus s2a minus s3 I is equal to 0. From this equation, we need to find out what is the A matrix. We obtain that A power 4 is the required solutions. And next to verify the Cayley-Hamilton theorem and find that. Verify means again that whatever the equation that is lambda square minus s1 lambda plus s2 is equal to 0. And again we need to replace at lambda is equal to a. That is a square minus s1a plus s2 I is equal to 0. And from this equation, we need to equate the satisfied. What is the find out a square and again a is a given matrix, I is a unit matrix. And based upon this one, again you need to find out in terms of a power 5, that is multiplication with 2, that is a power cube on both sides. Then we obtain that a cube, and further one by one it is a cube and again a power 4 and again a power 5. That is one by one we need to find out what is the a matrix. We obtain the matrix and again equation. We find the solutions. Using the Cayley-Hamilton theorem a power 8. Here also using that means that is a square minus s1a plus a2, that is s2 is equal s2 into I is equal to 0. Based upon this the characteristic equation, after that replacing lambda is equal to a square minus s1a plus s2, that is into I is equal to 0. And based upon this one, again we need to find out what is finding that s1 and also s2, then we find the solution. Whatever you get the equation, it is multiplication something a power 6 or something like that, we get the solution of a power 8 is a required solution. And here also the diagonal matrix is the matrix is the diagonalization or not. The matrix eigenvalues are lambda 1 comma lambda 2 comma lambda 3 is the 2 comma 2 comma 1, because of the matrix is the upper triangular matrix. Upper triangular matrix. If the matrix is the upper triangular matrix, the diagonal elements are the eigenvalues, that is 1 comma 2 comma 2. 1 is okay, but we need to find out what is the AM and also GM. That is particularly 2 AM is 2 and we need to find out what is GM, that is n minus, that is rank of A minus lambda I is equal to 0. And based upon here, we need to calculate if it is both are the same, it is a matrix is the diagonalization of the matrix. Next part B, that is a long type questions. One is the diagonalization matrix and find the A power 4. And here also the diagonalization nothing but we need to find out what is the D is equal to P inverse in AP. Here P is nothing but that is a x1 and x2 and x3. And we need to find out P inverse, the product of P inverse into A into P. We need to verify that is a diagonalization matrix. And find the A power 4. A power 4 is nothing but whatever you obtain that a cube minus s1 a square plus s2a minus s3i is equal to 0. In this equation, we need to multiply a, then we get that. Otherwise, that is a power n. Otherwise, that is a power n is nothing but p into d power of n into p inverse is the value. As we know that the formula. In that here, a power 4 is nothing but p into d power 4 into p inverse. We find the solutions. And determine the model matrix for p. Here also, we need to find out lambda 1, lambda 2, lambda 3. And again here, what is it? x1, x2 and x3. The collection of x1 and x2 and x3 is nothing but that is a model matrix. Next, to verify the Cayley-Hamilton theorem, this is also same a cube minus a square plus s2a minus s3i is equal to 0. Verify the Cayley-Hamilton theorem, first part, and second part multiplication with the A inverse, and third part multiplication with the A on these equations. We get the matrix is A inverse and also A power 4. And finally, find the eigenvalues and eigenvectors, that is data of A minus lambda is equal to 0. We get that lambda 1 comma lambda 2. And similarly, A minus lambda 1 I into x is equal to 0. We get that x1. And similarly, A minus lambda 2 into I into x is equal to 0. We obtain the x2. These are the eigenvalues and eigenvectors. Next, further calculate the eigenvalues, eigenvectors. Same, this is also above one in the fourth problem wise. And sixth one, verify the Cayley-Hamilton theorem and reduce that. Same, Cayley-Hamilton theorem means that is a square minus s1a plus s2 I is equal to 0. We need to satisfy. And a square find out with the help of a into a is a matrix. And from this equation, we need to multiply with a power 6. Then we get the solution. And further, eigenvalues and eigenvectors. Here all are same. The conditions. We need to find out what is the data of a minus lambda is equal to 0. And again find out lambda 1, lambda 2, lambda 3, x1, x2, and x3. And again, eigenvalues, eigenvectors. A power inverse is nothing but from this a cube minus s1a square plus s2a minus s3 I is equal to 0. From this equation, we need to find out multiplying with a inverse multiplied with a. We get the a inverse and a power. Diagonalization of a matrix is also additionally am and gm. We need to check the conditions. Otherwise, linearly independent. That means different eigenvalues. Eigenvalues is also the matrix is the diagonalization is existing. All are same. The conditions. Data of a minus lambda is equal to 0. Find out lambda 1, lambda 2, and lambda 3. Corresponding x1, corresponding x2, x3. Then find out same like that. A cube minus s1a square plus s2a minus s3i is equal to 0. And in this, multiply with a, then you get a inverse. After finding s1, s2. Yeah, similarly, these are also like same the concept of eigenvalues and eigenvectors. That is data of a minus lambda is equal to 0. Lambda 1, lambda 2, lambda 3, x1, x2, x3. A cube, a square. From this equation, 2a square take out common from here. Diagonalization means d is equal to p inverse into ap. To find the solutions. These are the clearly finding the diagonalization of a matrix and inverse of the matrix and verifying the Cayley-Hamilton theorem and finding the eigenvalues and eigenvectors. And these are also same the Cayley-Hamilton theorem, eigenvalues, equation, inverse. Diagonalization of a matrix, it is d is equal to p inverse into ap. We need to find out the eigenvalues and eigenvectors, and again inverse of the matrix and find the matrix. Characteristic equation, multiplication with a, we get the solutions. And here also same the condition of above, same the conditions. Here verify that. That means a cube minus s1a square plus s2a minus s3i is equal to 0. Find out s1, s2, and s3, a square, and a cube. Yeah, and finally, that is a short type questions. Find the eigenvalues and eigenvectors. It is also nothing but data of a minus lambda is equal to 0. That means that is 4 minus lambda, 1 minus 3i, 1 plus 3i, and 7 minus lambda. We need to find out what is the lambda 1 and lambda 2. State Cayley-Hamilton theorem. That means every square matrix satisfies its own characteristic equation. This is the statement of the Kelly-Hamilton theorem. And find the eigenvalues and eigenvectors of this is the matrix by the property. If A is equal to, as we know that lambda 1 comma lambda 2, and A square is nothing but lambda 1 square and lambda 2 square, and A cube is nothing but it is a lambda 1 cube and lambda 2 cube. But in this matrix, here the lambda 1s are 2 comma 1, again 2 square comma 1 square, it is a 2 cube comma 1 cube, and you need to replace in this equation, you get the solutions. It is a 2 square, by the property we need to apply here, 2 square and 2 cube. Define the model matrix and spectral matrix. Model matrix is nothing but P is the, that is x1 comma x2 comma x3. How to define means the collection of eigenvalues is called, the collection of the eigenvectors are called the model matrix. The spectral matrix is nothing but that is a P inverse into A into P is a matrix. It is a model matrix and it is a spectral matrix. Then the resulting diagonal matrix is called, that is a spectral matrix. If find the eigenvalues are this one means adjoint of A. As you know that adjoint of A is nothing but that is A inverse is equal to, that is adjoint of A by A, that is data A. Adjoint of A data is nothing but A inverse into, that is the data of A. That A inverse is nothing but 1 by comma 1 by 2, 1 by 3, 1 by 4 into the data of is nothing but 2 into 3 into 4. It is nothing but 1 by 2 comma 1 by 3 comma 1 by 4 into, that is a 4 3 is a 12, 12 2 is that is 24. It is nothing but that is 12 comma 8 comma that is a 6 is the eigenvalues of the adjoint of A. Find the sum and eigenvalues. The sum is equal to, as you know that is a trace. It is equal to 2 plus 3 plus 2 is nothing but that is a 7 value. These are the whatever we understood the previous, that is a formulas and concept and everything, then here easy to solve the problems. Verify the Kelly-Hamilton theorem. That means we need to find out that is a square minus s1a plus s2 is equal to 0. That is s1 is equal to, that is a trace, and s2 is equal to, that is the data of the matrix. Next one, show that the vectors are, that is a linearly dependent. As per the linearly dependent is nothing but we need to find out what is the data of A is equal to 0. That means 1 1 2 and 1 2 5 5 3 4 is equal to 0. Find the characteristic matrix. That we need to find out what is a is equal to 0. That is A square minus lambda square minus s1 lambda plus s2 is equal to 0. Here s1 is a s1 lambda cube, s1 lambda square, s2 lambda minus s3 is equal to 0. Minus s2 lambda plus minus s3 is equal to 0. And here find out lambda 1, lambda 2, not find the equations. That means s1, s2 and s3. As you know that s1 is a trace and s2 is the sum of the cofactors of the diagonal, and s3 is the determinant of the matrix. Define the linearly dependent and independent. Linearly dependent is nothing but that is a data A is equal to 0. Linearly independent is nothing but the data A is not equal to 0. Find the eigenvalues of the matrix, and here also A minus lambda is equal to 0 is nothing but 3a minus lambda 2 plus I and minus 2 plus I minus lambda is equal to 0. We find out what is the lambda 1 comma lambda 2. These are the finding the procedures. And here also show that the matrix are linearly dependent. The linearly independent is nothing but it is 2 comma 2 comma 1 1 4 minus 1 and 4 6 minus 3 is data is not equal to 0. Define the characteristic equation, that is data of A minus lambda I is equal to 0. For example, 2 by 2 lambda square minus s1 lambda plus s2 is equal to 0. Otherwise, lambda cube minus s1 lambda square plus S2 lambda minus S3 is equal to 0. That is under the 2 by 2. This is the 3 by 3. State the eigenvalues and eigenvectors. Eigenvalues is nothing but the data of A minus lambda is equal to 0. The 3 by 3 lambda 1 comma lambda 2 comma lambda 3 are the eigenvalues. X1 comma x2 comma x3 are the eigenvectors. That is eigenvectors. Find the characteristic values of the matrix. That means the data of A minus lambda is equal to 0. That is 1 minus lambda 2, 2, 1 minus lambda is equal to 0. We need to find out what is the lambda 1 comma lambda 2. Because of the matrix is the 2 by 2. And here also for the matrix A and also X, then you find out A is given, and again from A to A square we need to find out multiplication X and again Y, then find the solutions. And again hence find that A inverse is also find the solutions. A inverse is nothing but argent of A by delta A is the conditions. Find the eigenvalues of the matrix. The data of A minus lambda is equal to 0. That is data of 1 minus lambda 4 and 3, 2 minus lambda is equal to 0. Find the values are eigen lambda. Whatever we get after getting these values, for example, if we get like lambda 1, lambda 2, like any values, the sum is equal to the trace and product is equal to the data of the matrix. And further, linear independent. The linear independent is nothing but the data is 1 0 0 0 1 0 and 0 0 1 is not equal to 0. Find the sum and product. The find the sum and product is nothing but the sum is equal to the trace A and the product is equal to data of the matrix. Next, finally, it is determine the characteristic roots, and here also the matrix is the upper triangular matrix. Upper triangular matrix. Therefore, the diagonal elements are eigenvalues by the property minus 2 comma 3 comma 1. Since by property. Otherwise, we need to find that we need to find out data of A minus lambda is equal to 0. We need to find the solutions. These are the eigenvalues of the matrix. These are the like critical thinking and also the essay type questions, and also finally it is short type questions under the module 2, that is eigenvalues and eigenvectors. I hope everybody understood regarding this the question bank. The totally we covered here the formulas and again the basic definitions what are the occur in the module 2, that is under the eigenvalues and eigenvectors. Wish you all the best. And further in the next session we will go to discuss the module 3, that is a general mean value theorems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.